This might just be the best printer you've never heard of. It's called the Marathon, and for good reason. It's not the fastest printer on the market, but it's got the stamina to go the distance. It's built to last. If you have heard of it before, it's likely because you've seen one of my two previous videos on it. The first, in which I interviewed its designer, Dr. Dan Marinescu, or the second, in which I unboxed and assembled it. Links to those below in case you missed them. The Marathon is unique for a variety of reasons. It's not just another printer rushed to market by one of the usual suspects in a race to the bottom. On the contrary, Marathon was thoughtfully designed by someone who cares, and it shows. From the hardware to the firmware, everything has been carefully considered. Marathon is offered for sale by Formbot, aka Vividino, a company best known for their Voron kits or mostly pre-assembled Voron clones. It's Dan's design. They've just helped him to commercialize it and bring it to market. This is the part where I disclose my biases before we proceed with this review. This was provided free of charge by Formbot, and I will get a small commission if you decide to purchase one using my link in the description. But I wasn't paid to make this video, and the opinions expressed here are my own. I didn't know Dan before learning of the Marathon, but I have since had many conversations with him and developed good rapport. That won't stop me from being honest about the shortcomings of this printer, but there's a higher likelihood that I'll phrase them in a more constructive way on account of my familiarity with the designer. With that out of the way, let's dive into it. So what makes Marathon different? Well, for starters, it's an IDEX printer. It has two independent toolheads. This gives it the ability to do multicolor printing with minimal waste, or to do multi-material printing with no cross-contamination. Mixing, for example, PETG and TPU to combine rigid with flexible, or PETG and PLA for easy support removal, taking advantage of the fact that these dissimilar materials don't adhere to one another. It can accomplish these tasks much more efficiently than an AMS-type system, for which the entire contents of the hot end must be purged when switching between filaments. Only a small amount of purge is required to prime the nozzle when switching tools. With a bit of tuning, zero waste is also possible, eliminating the purge tower and filament poop altogether. But it's not only more material efficient, it's also much quicker, with only a few seconds required to switch between filaments, as opposed to a minute or more. The efficiency is equivalent to a tool changing system, but IDEX printers can also do a few things that a tool changer can't. A tool changer only ever has one active tool, with the unused tool remaining parked. On an IDEX, both tools can be used simultaneously. Each tool has its own X-axis motor, but they share a Y and Z axis, so we can't print two completely distinct objects. We can either print two identical copies of the same model, or one that is a mirror image of the other. The Marathon is an IDEX printer, but it's not the first to exist. It's not even Formbot's first IDEX. It's preceded by the T-Rex, a supersized bed slinger running Marlin firmware. The Marathon runs Clipper. It's not quite as big as the T-Rex with its 400 by 400 bed, but the build volume is respectable. 335 on X, 300 on Y, and 290 on Z. For comparison, the Snapmaker J1, another notable IDEX printer, is only 300 by 200 by 200. The closest comparison is the Ratrig VCore 4 with the IDEX upgrade. The 300 cubed variant comes in at a little over $1,300 before adding the IDEX upgrade, the pricing for which is currently unknown. The Marathon is currently selling for $1,269 and comes pre-configured with two toolheads, which makes the pricing very competitive. The VCore 4 is a nuts and bolts kit. The Marathon is mostly pre-assembled. The quoted assembly time is 3 hours, which I'd say is pretty accurate. It's a series of straightforward steps, with none being particularly difficult, but some, like the installation of the acrylic panels, being tedious. The printer is fully enclosed, with a pivoting top lid and hinged front doors. The interior volume is large enough to accommodate two 1 kilogram spools. It comes stock with rear-mounted spool holders, but they're inconvenient to access. Instead, the hardware from those can be repurposed and combined with some printed parts to make these interior spool rollers. Not only are these more convenient, but the heat from the chamber will help keep the filament dry. This is one example of how Dan took some of the early feedback and used it to make this printer better. The motion system on the Marathon is quite unique. It's not a bed slinger and it's not Core XY. It's similar to a Cartesian motion system in that X and Y are independent of one another, but it's not that simple. The Y-axis is belt-driven with two linear rails, each with a dual carriage for added stability. The X-axis is where things get interesting. Rather than having the motors rigidly mounted to the frame with torque transferred through a belt, The motors move with the tool head, while the belt remains stationary. So that's neat. But what will no doubt raise some eyebrows is the fact that there's no gantry to speak of, no aluminum extrusion for the x-axis. There's simply a linear rail and nothing else. You might be concerned that this would deflect under the weight of the tool head, and that would be valid. Dan has considered this and has done the appropriate simulations to demonstrate that the deflection is minimal. But is the reduction in weight worth the loss in rigidity? To answer that, let's take a look at the input shaping results. There's no onboard accelerometers, so I had to add my own. These are the results for the y-axis of each tool. They came out looking almost identical. The recommended shaping function is ZV with a maximum acceleration of 8900. For comparison, here are the results for 3 other printers: the Qidi X-Max 3, X-Smart 3, and Q1 Pro. Marathon has the highest recommended acceleration among them. The Y might be above average because of the reduced weight in the absence of a gantry. The results for the x-axis weren't identical between tools, but both had clean graphs with high recommended accelerations: 17,400 for tool 0 and 10,600 for tool 1. There are no significant components of vibration in the z-axis on either the x or y graphs, which seems to indicate that the rigidity is sufficient, even in the absence of an x-axis aluminum extrusion. The way input shaping is handled on an IDEX is different than a regular printer. The position of the second tool will affect how the first one resonates, and vice versa. For this reason, there are distinct shaper parameters for each of the different printing modes: single tool, mirror, and copy. The default values seem to work okay, with only slight ringing visible on the sharp edges of glossy prints. Alright, back to the kinematics now. The z-axis is driven by 3 ball screws, each with an independent motor. This enables kinematic bed leveling, ensuring the bed plane is perfectly parallel to the gantry. Note the use of the higher quality ball screws as compared to the more common lead screws. Each ball screw also has a version of Mirage C's Wobble X, which decouples the lateral motion of the screw from the vertical motion of the bed. This is intended to eliminate any Z-banding that would otherwise result from imperfections in the ball screws. The bed itself is 8mm thick cast aluminum with a 650 watt silicone heating mat, capable of reaching 120 degrees C. A super Pinda probe mounted to tool 0 is used for mesh generation. The mesh reveals that the bed isn't particularly flat, with a notable dip in the middle and an overall deviation of approximately 0.3mm. This is well within the range of what could normally be accounted for using mesh compensation, but there's an extra consideration here. When printing in copy mode, tool 1 copies exactly the moves of tool 0. This includes the z-axis motion. Any dynamic height adjustments to account for bed flatness will be applied to both tools. So the adjustments will help with the first layer of tool 0, but they could well make that for tool 1 worse. This makes having a flat bed even more important on an IDEX printer. Despite the less than perfect bed flatness, the first layer still came out okay in my testing when printing in mirror and copy mode. Each tool is equipped with an Orbiter V2 extruder and an integrated runout sensor, which has to be one of my favorite features of this printer. There's a status light on top that changes from green to red when filament runs out. When filament is fed in, it will start loading automatically. If you want to switch the filament, a button on top initiates the process, first heating the hot end and then unloading. These runout sensors saved me quite a few times as I was dealing with brittle filament, breaking in the PTFE tube, pausing the print and allowing me to reload it before continuing. Part cooling is accomplished with 2 4010 radial blower fans. The fan ducts appear to be well designed with a good amount of airflow. For the most part, overhangs were sharp with minimal curling. It was only at the upper limit of print speeds with steep overhangs that the cooling was slightly lacking. The hot ends are from Triangle Lab. They have a bimetallic heat break and a 50 watt cylindrical ceramic heater, capable of reaching 320 degrees. In my testing, they achieved a maximum flow rate of 21 mm³ per second with standard PLA. What's interesting about these is that the heat break is smooth, not threaded. It's held in place by 2 grub screws. The nozzle and heat break are combined in a one-piece assembly, similar to the Revo ecosystem. This has the benefit of preventing leaks, but the primary function on the Marathon is to adjust the relative height of the nozzles between tools. When printing in mirror or copy mode, it's not possible to apply a software offset to the z-axis for one tool without also affecting the other tool. Therefore, the nozzles must be adjusted mechanically to ensure they're at precisely the same height. This involves loosening the grub screws and dropping the nozzles down to the bed before retightening them. That takes care of the Z offset between tools, but it's also possible that they'll have an X and a Y offset. The calibration of those offsets becomes important when using both tools in a single print. We want the extrusions from tool 0 to perfectly coincide with those from tool 1, such that there is no gap and no overlap. In order to determine these offsets, we have two options. The default is to print a calibration model, which acts as a ruler of sorts. By identifying which tick marks are aligned, we can determine the offset between tools. Once the values have been determined, we enter them in the web interface. It may be necessary to print this a few times in order to validate the results. This process is easy enough, but if it sounds too laborious for you, there's another way. Instead of the manual calibration, we can do automatic calibration using a camera to determine the offsets. This is an aftermarket upgrade which makes use of the CXC Camera from Ember Prototypes. The software side of it is a group of Klipper macros called kTAMV, which stands for Klipper Tool Alignment using Machine Vision. This doesn't come with the stock hardware, but Dan has written a detailed guide on how to install it and set it up. He provided an STL file for mounting the camera and pre-installed all of the macros for kTAMV. In order to activate them, we simply need to uncomment the corresponding lines in our printer config. The newly available Auto Tool Align macro prompts the tools to move over the camera. Machine Vision is then used to pinpoint the precise location of each nozzle, thereby determining the offset between them. The result is faster and more precise than the manual method. But if you account for the time required to set up the camera, the only real benefit is a few extra decimal points of precision in the measurements. With the offsets determined, we can get up and running with some multi-tool prints. If this is your first time working with a printer that doesn't poop when changing colors, you'll no doubt be amazed at just how quick the tool changes are. The print quality is good. The profiles could use some tuning to reduce stringing, but it's a good starting point. Much better than what I got from my initial prints on the Prusa XL. Slicing for the Marathon happens in Prusa Slicer. There's 3 different profiles, one for each of the different print modes. Dan has also provided a set of print profiles and filament profiles. As compared to the Bambu Lab X1C, the print speeds are 20 to 40% slower depending on the feature type. In the speed profile, the accelerations are actually higher, 15,000 for travel moves and 8,000 for external perimeters, as opposed to 10,000 and 5,000 on the X1C. The net result, combining the slower speeds with the higher accelerations, are print times that are an average of 30% longer on the Marathon. But the equation gets flipped when accounting for filament swaps or when printing in mirror or copy mode. In those cases, the throughput of the Marathon far exceeds the X1C or other similar printers. Let's loop back now to the hardware of the printer and cover something we missed before: electronics. The main board is a Bigtree Manta M8P with an onboard CB1 that handles the Klipper computations. Downstream of that are the toolhead boards. These are custom for the Marathon. They're connected to the main board via a bus cable and have a variety of connection points for the various toolhead electronics. The interface to the printer is a small touchscreen. Emphasis on small. It's the Bigtree TFT35 SPI. This is one of the only real complaints I have about the hardware. The screen is undersized. It requires a stylus to operate. Most of you will probably prefer to interact with the printer through the web interface instead. But if you're the type that prefers a physical interface, you're in luck. Dan has written a guide on how to install a larger 5-inch HDMI touchscreen. You can download any of these guides and the associated assets directly from within Mainsail. And this brings us to one of the best parts of the Marathon, the firmware. It's running Klipper, which is pretty much par for the course these days. But more often than not, the implementation is sloppy at best. An outdated version of Klipper has been forked, or the layout of the configuration files is confusing and hard to navigate. I think that describes most of the Klipper implementations I've seen from the major manufacturers. Dan has taken a different approach with the Marathon. He sought to emulate the structure of RADOS. If you're not familiar, RADOS is the Klipper implementation used on RATRig printers. It's highly organized and structured in such a way that it's difficult to break. The core configuration files are all read-only. You have to copy the corresponding config sections to the main file in order to modify the parameters. All of the configuration files can be updated directly through the Update Manager by updating the RADOS package. The process is the same on the Marathon. Updating this package updates all of the configuration files and all of the upgrade guides and other supplementary materials. Anytime Dan makes changes, you can fetch them automatically just by clicking this button. The main configuration files are read-only and are logically organized into folders. If you want to modify the configuration, you simply need to create your own file, which is then imported into the main printer config by uncommenting the indicated line. For instance, I wanted to modify the behavior of the chamber fan, so I copied that config section and pasted it into my own config file, before modifying the parameter I was interested in. I must say that in my opinion, this firmware implementation is exceptionally well done. Over the course of my time evaluating the Marathon, I did a variety of tests to evaluate the performance in each of the different print modes. Having never worked with an IDEX printer before, I was most impressed by the mirror and copy modes. The throughput was double that of a normal printer, effectively making the Marathon 2 printers in one. The obvious limitation, however, is that the build volume is halved. We still have 300 on Y and 290 on Z, but only 168 on X. I mentioned earlier how when printing in one of these modes, the bed leveling from tool 0 is applied to tool 1. The same is true of the filament parameters, specifically temperatures and extrusion multipliers. It's not possible, as far as I can tell, to separately define these values for each tool. What this means in practice is that we can't load each tool with a completely distinct filament and expect to get good results. But as long as the filaments are the same or similar, it's a non-issue. Of course, the printer can also be used in single tool mode as well. In this case, the unused tool simply remains parked out of the way. When parked, a compliant metal strip seals the nozzle to prevent filament ooze. Any ooze that does occur is taken care of before the print by brushing the nozzle over a brass brush at the rear of the bed. This is a nice feature, and something that is sorely missed on the Prusa XL. Without the brush, the ooze ends up being dragged across the bed, while also wrecking the accuracy of the bed mesh since the nozzle is used for probing. There's a community mod to add brass brushes, but it really should be included as stock hardware. Among the single material test prints I conducted was the mounting bracket for the CXC Camera, printed in ABS glass fiber. The nozzles are hardened steel, so abrasive filaments are no problem. The Marathon is equipped with a chamber thermistor to monitor the internal temperature. There's no chamber heater, but there is an exhaust fan, complete with a carbon filter. The chamber temperature rose rather quickly to around 55 degrees, at which point the exhaust fan kicked on to try to cool it back down to a set point of 45. This behavior would be good for PLA, but for ABS, we want to keep as much heat in as possible. After some digging, I found that the set point is passed as a parameter from the slicer. I increased the value from the default to prevent the fan from turning on and saved the change to the ABS profile. The result looked good with no warping. I then attempted some multi-material prints. This is something I tested extensively on the XL, combining different materials to take advantage of their unique properties. The knowledge I gained transferred directly to the Marathon. There's a few lessons to be learned that you'll need to apply, specifically when combining two dissimilar materials like PLA and PETG. This is a popular combination because it allows you to have a zero-gap interface, using the PLA as support for PETG or vice versa. This yields clean surfaces with easy-to-remove supports, similar to a soluble support material, but without the cost premium. Another popular combination is PETG and TPU. These stick very well to each other, so adhesion is not a concern. In my initial attempts with TPU, the filament was getting tangled in the extruder. I reduced the idler tension, and from that point forward, it printed without issue. It's certainly fun and functional being able to combine rigid and flexible in the same print. One other application of IDEX that warrants mentioning is the ability to use one tool for the perimeters and one for the infill. In this way, a more expensive aesthetic filament can be reserved for only the exterior shell of the model, with the remainder being printed in a less expensive generic filament. You also have the ability to put a larger nozzle size on the dedicated infill extruder, increasing strength and reducing print times. So that's the Marathon in a nutshell. It's a solidly built machine with good hardware and great firmware. It prints equally as well as the most popular single tool printers, but it has the added benefit of a second tool head, giving it the ability to efficiently combine multiple colors or materials, or to use both tools in parallel, doubling the throughput. The biggest drawback is the size. It's hefty and has a large footprint. The requirement to move the unused tool fully off the bed means that the build volume is small relative to the machine volume. The kinematics have pros and cons. The Y-axis design seems sound, despite its eyebrow-raising appearance. The inclusion of the X-axis motors in the printhead reduces complexity, but I question whether it's worth the trade-offs. Even with the motors engaged and the currents overclocked, the tools are fairly easy to move by hand, seeming to indicate that the torque output of these small motors is lacking. I had some layer shifts throughout my testing that could be mitigated by reducing the accelerations or increasing the motor current. The default motor current already exceeds what is recommended for these motors, so I wouldn't want to go any higher and risk decreasing their lifespan. So it seems that this design will have a definitive upper limit on acceleration as a result. A threshold of 10,000 seems suitable, so long as sharpness of details isn't of paramount importance. This puts the Marathon on par with other high-speed printers, just not ultra-high speed. But I'd love to know what you think. Do you like Dan's design, or do you see room for improvement? I personally feel that it's great value in today's market, and has a lot of potential to be a useful tool for a lot of people. Please share your own thoughts down in the comments, and while you're down there, do me a favor and hit that like button if you enjoyed the video. And if you're not already, subscribe so you don't miss my future videos. Thank you guys so much for watching. My name's Taylor, this is YGQ3D, and until next time, happy 3D printing.